Finally, we extend natural deduction to first-order logic. Universal elimination is straightforward from for all x, a of x. Instantiate any term t to get a of t. Universal introduction is more delicate. If you prove a of c for an arbitrary c, and c does not depend on any undischarged assumption, then you may conclude for all x, a of x. The arbitrary condition is essential, otherwise one special example would incorrectly prove a universal statement. Existential introduction is simple. If you have a witness t such that a of t holds, you may conclude there exists x such that a of x. Existential elimination is more careful. From there exists x such that a of x, introduce a fresh name c, assume a of c, and derive your target conclusion c. The name c must not appear in c, because the final conclusion must not depend on the particular witness chosen. In sequent calculus, quantifier rules come in dual pairs. For all left and exists right may use any concrete term t. They are specific rules. For all right and exists left require a fresh variable a. They express arbitrariness. Notice the symmetry. Existential on the left behaves like universal on the right, and universal on the left behaves like existential on the right. Freshness conditions are not cosmetic. They prevent invalid reasoning. If for all right did not require freshness, one could fake a proof of there exists x such that a of x implies for all x, a of x, which says that if one object satisfies a, then all objects satisfy a. That is plainly wrong. The rules carefully separate arbitrary objects from particular witnesses. Consider for all x, p of x implies q of x, and there exists x such that p of x together imply there exists x such that q of x. From the existential premise, pick a witness c with p of c. From the universal premise, instantiate to get p of c implies q of c. Then derive q of c and introduce there exists x such that q of x. For the second example, there exists y such that for all x, p of x, y, implies for all x, there exists y such that p of x, y. If one y works for every x, then for each x there exists a y that works, namely that same one.